Okay, so this one I'm going to roll through pretty quickly, I feel like. This is special right triangles. Number 2. And this one deals with the 30, 60, 90. Okay, let me ask you some questions right off the bat. What does this 30, 60, 90 mean?
Those are the angles
Of?
of right triangle.
I mean, that's pretty much it. Yes, I don't know if I could say it differently. Did you hear what she said? Those are the angles of a right triangle, right? So here it is, and let's draw it. Okay? So thank you. I mean, that takes us down the road a long way, right? We go straight into the 30, 60, 90. Why do we like this triangle so much? Because the side ratios come out the same all the time, and it's an even, kind of a common situation. We could set up a lot of things in construction or engineering with the 30, 60, 90, and we can solve all the sides as long as we have one because we know the side ratios. Okay. How about the sum of the angles? Do you see what 30 and 60 add up to? 30 and 60 is how much? Yep, you're jumping ahead of me, but yes, I was going for 30 and 60 are 90, and the other 90 is your 180, right? And that's the total number of degrees in a triangle. That's the one thing you don't want to forget and keep in your mind because that's sort of the magic number. Okay, do you remember the side ratios of the 30, 60, 90? We'll do like a place. You're going to need to place an x, you're going to need to place a 2x, and you're going to need to place an x times the square root of 3. So it's like move them into their places. One goes to this side length, one goes to this side length, and one goes to this. Which is which? And I'm doing it in the same order we did last time. So I'm hoping your brain links that up and puts them in. So x, and that can't change. X is on the opposite side from the 30 every time, all the time. It does not change. This side?
2x.
Okay. And this side?
X radical 3.
Okay, nice. So this is your pattern. It's your mold. It's your, whatever you call something that defines the whole thing, right? It's the instructions. It's the key. Anything like that, it tells you what to do, right? So, and now I'm just going to roll through 3 examples like we did before. So this looks a lot like the prior lesson. Originally, I had it set up to examine the opposite side, I think. This one, I think I did opposite, then I did adjacent. I kind of forget. But lesson number 2, let's just roll through 3 30, 60, 90 triangles. Here's one, 30 degrees. Here's another, 30 degrees. And here's another. And 30 degrees. We don't have to label the 60. You know it's 60 already because you can just add them all up, subtract from 180, and you know it's a 30, 60, 90. Fair enough? So if you saw a triangle that was right, and only one angle was dropped in of the other 2, say it was 60, you would know that's a 30, 60, 90 also. Fair enough? Okay. So then, let's come up with some numbers. How long do you want to make, let's guess, let's just come up with a number. How long do you want to make this side? Give me a number.
23.
I like 7 better.
What did you say?
23.
Oh.
I'm just going for simple. All right, if this is 7, let's go to the more difficult side. How long is this side over here? Don't say this yet. Sorry. How long is this side down here? Okay, how long is this side up here? Why? Does this make sense, Brianna? Marisol? The pattern says, whatever you tell me the length of this side is across from the 30, then I know that the hypotenuse, the one not touching the 90, is 2 times that. So you tell me this one's 7, that one's got to be 14. Fair enough? Okay, jump down to this one. How long is this side here? Good. Does this make sense to you? Did you hear what she said? She said 7 times the square root of 3. So see the pattern? The pattern is whatever this length of this side is, we just multiply it by the square root of 3, and that's the length of this side here. I know, kind of crazy, right? Does this make sense? Okay, so the 7 just drops in, 7 times the square root of 3, and it sounds very much like we know something very exciting, because that's kind of elaborate now in terms of the math we might have known before, right? Square root of 3 is just a number, it's irrational. You can type it into your calculator and do square root of 3 times 7 and get a number, but we're gonna leave it in the square root format, because if we type it in our calculator, it produces all the decimals, which go on forever, and then we cut them off at some point. We actually create error when we do that. By leaving it under the square root symbol, it's infinitely accurate. Does that make sense? So now, you don't even have to calculate things anymore. You leave them in sort of their raw form, and they're more accurate than before. Same thing with pi. We don't drop in 3.14 anymore. We just leave pi in there, because it contains all the infinite decimals behind it. We can't write them, but we can write pi, and all of the decimals are with it, right? Well, I guess the number's to the right of the decimal is what I'm trying to say. Okay, that's fabulous. All right, now your turn, Carrie. Give us this one. Let's see how difficult you're gonna make it for us.
13.
Oh, look at you. You picked an odd number. All right, 13. That's all right, I'm sure we can do it. All right, so what's this side over here? What do you think, Marisol? What did we do when we had 7 here? What did we do to get to 14? Good. In your mind, what is the reverse of multiplying by 2 in math? By? 6.5. Fair enough? Trust yourself, Marisol. Do it. Good. Good. 6.5 times the square root of 3. And you can type it in your calculator. Just say 6.5 times 3 square root, or however your calculator works, right? The iPhone's a little bit backwards. The Android's forwards. Doesn't matter. That's a whole number there that we could calculate. Otherwise, we just say 6.5 times square root of 3. And so Carrie picked one that when we divide it by 2, created a decimal. But so what, right? We could have put 6.5, but now we put 6.5. Same thing. Okay, let's go for the more difficult one. I'm going to help you pick this one because I have something in mind. I want to see it. I want it to reduce as we go through the process. So I'm going to pick something divisible by 3. All right. Yesterday or the prior lesson, I picked 12. I'm going to pick 15. So let's say this side's 15 long. This is the most difficult side if they give us this. The thing you have to remember is how, number one, how to set it up to solve it. How do I set this one up to solve it? And this one's difficult. I'm giving you that, okay? This one is very difficult. And I'm not sure that our brain always links this up.
You say 15 equals x radical 3.
Say it a little bit louder. 15 equals?
X radical 3.
Yes. So, she's saying 15 equals, well, let me write it so you can see it. 15 equals x times the square root of 3. Why? Because the pattern tells us that whatever x is here times the square root of 3 has to now be equal to 15 for this problem. So whatever x is, if we can figure out x here times the square root of 3, that results in 15. This x will then be the length of this side, and we'll multiply that by 2 to get the length of this side. And if I drew this right, if I drew the 30 degrees pretty good here, This measurement is 2 of them up here, right? 2 links. This link times 2, so it's 2 of those links, right? Physically speaking, just to get that sort of ratio. This ratio and this ratio are a little bit easier to understand than this one. Our brain doesn't our brain doesn't really think this way yet. You probably have to do a lot of these before your brain did, right? But 2 times, we can think that. We can think of, I have 1 large fries from McDonald's and now I got 2, right? It's just very straightforward for our brain to think. So I had this many fries and now I got double, right? And okay, so let's flip it. Because I want the x on the left side to solve the equation. And the only way I think for you to try to understand these is to actually take a few, and I would use the same problem in your composition book, and I would write a few out. You're refusing to look at me, but I'm looking at you.
Sorry, it's because you have 13.
It's what?
You have 13.
Oh, you are on. Nice, thank you. I just write stuff. I just start writing. But I want you to practice this in your composition book, this very problem, and practice the algebra and see if you can do the algebra the same way, right? At our school, where we put geometry before algebra, we did a good thing because I believe that students struggle more in algebra, so moving it to the 10th grade year I like a lot. But we did a bad thing because a lot of the algebra you would have learned about how to solve this equation, you now don't really know yet or haven't practiced much yet. With me? So it's good and bad, but like a lot of things. Okay, in equation solving, there's a line down the middle of the equation. There's a left side and a right side. Whatever you do to one side, you must do to the other. That keeps the equation balanced and equal. If you change that, if you do something to one side and not the other, we've now changed the structure of the balance. So we have this thing of isolating the x as the language teachers will use. So if this is being multiplied by a square root of 3, the way to reverse it, just like you said, the reverse of multiplying by 2 was to divide by 2. The reverse of multiplying by square root of 3 is to divide by square root of 3. If I divide this side by square root of 3, square root of 3 over square root of 3 disappears because it becomes 1. It's like saying 1 times x, so you're left with x. What you do to one side, you must do to the other. I'm so badly wanting to write 13 in there, I'm not sure why. Now we can get rid of these cross out, but now we have this problem on the right side. We have this square root in the denominator position. It's illegal in math. There are rules in math that say you must simplify. We don't want to see a radical in the denominator position, so we must do the process of rationalizing the denominator. I can't even say it. Rationalizing the denominator, right? Okay. What do we multiply this fraction by to rationalize it? Say it louder. 1 is a good answer. 1 is right. Can you tell me more? Like, do I literally write a 1 here? How do I write it? Yes. Nice. Radical 3 over radical 3. Why is it 1? Why is that 1? Okay, how about this? Why is this 1? 5 over 5. Isn't that 1? Why? Because 5 divided by 5, it goes in 1 time, right? So any number over itself, other than 0, by the way, any number over itself, including square root of 3 over square root of 3, is 1. Fair enough? Okay, good. You're saying all the correct answers, and I think you understand what's behind it, but it's not an easy concept. This is not a normal sort of way of thinking. So now we get to so we can multiply anything by 1, and that's legal. If we have a $1 bill and we multiply by 1, how much you got? You still got the $1, right? So we can multiply anything by 1. It changes, why? What are we doing? We're changing the way it looks. Remember, if you have 3 over 6, that looks one way, right? But what is 3 over 6? 1 half. Don't they look different? But aren't they the exact same value? So if I have 4 quarters in this hand and a $1 bill in this one, don't they look very different? Means one's coins, one's a dollar bill. But the value of those, you go to the store and you buy something, you can use either one for the exact same value. Make sense? So what are we doing here? This whole simplification process, you're changing the way it looks, but you are not changing the value. We're maintaining that value of the number. So in this case, 15 times square root of 3, they cannot be combined, so they just sit next to each other with a times between it. Square root of 3 times square root of 3, the 3 times 3 becomes 9, and the square root's still there, so it's square root of 9. What is the square root of 9? 3. So it simplifies in the denominator position, and notice that's exactly what we're trying to do with the rationalized process. We now have gotten rid of the square root in the denominator. Hey, it moved up top, but we're okay with that, right? It moved up to the numerator position, but that's fine for us. So it comes over 15 square root of 3, 15 divided by 3, 3 divides into 15 how many times? 3 times what is 15? 5. So this equals, and I'm just going to come down here and say x equals now 5 times the square root of 3. This is now the value of x. And so we rationalize the denominator. We got that out of there. We have now solved for what x would have to be if it were multiplied by square root of 3. And so now, how long, and I wish I had moved this a little bit further away there. How long is this side of the triangle now?
5.
Marisol, how long is this side of the triangle? Tiffany, how long is this side of the triangle? So, don't make this too hard, okay, right here. This is the hard part. We did a lot of work. But what's this say right here? This side is x, and we solve for x, and it is 5 radical 3, so that's this side length. Carrie, does that make sense?
Oh.
It's the whole thing. I know why you're saying 5, because your brain's thinking like when I did this side, I just dropped in the 5 in front of it, and it was 5 radical 3, right? Is that kind of what you're thinking? But no, in this case, for this triangle where this is 15, this is 5 radical 3, because that's what x equals in this case for this situation. Is this okay? Okay. Can you double it? Marisol, what's 2 times 5 radical 3? Good, I love it. I love your brain. I love your brain. I can just see it working. That's awesome.
I want to say 10.
And you would be right. Look at the pressure. Good job. And way to stick with it, right? Way to sit there and let your brain sort of work through it and then trust yourself enough to say it even though you're not sure, right? Remember, I don't think humans learn anything without making mistakes. And I think one of the problems of our educational system is we kind of punish mistake making. You know what I mean? This is the completely wrong idea for humans to learn, I think, right? So you guys have to push yourself to a limit to that vulnerable point, right? And we all know what it's like to be in a class where you feel like you answered incorrectly, right? Sometimes that's a terrible feeling. And so we avoid it at all costs. But this is really what you have to, sadly, I think you have to ignore a lot of what we've taught you and still go back and be vulnerable enough to make mistakes, right? To try. So kudos for that and good job. And yeah, you'd think it'd be more complicated than that. But if 5 turns into a 10, it is doubling, and it's just being multiplied by the square root of 3 in both cases, so this has to be twice as much, if that makes any sense at all. So it has to be. So this is the length of this side, 10 radical 3, 5 radical 3, and I want to do one last thing. Try to prove to you that x is equal to 5 radical 3 for this situation. If this is x, then I should be able to drop it into this setup, x times radical 3, and when I multiply 5 radical 3 is x, right? And now I'm multiplying it by radical 3. I should get 15 as the length of that side. Does that make sense? So what is radical 3 times radical 3? It's 5 times radical 9. What's radical 9? 5 times 3. What's 5 times 3? 15. Check. The formulas all still work. The pattern still proves that if this is x, and you drop that in right here to x, so that would be that times radical 3, which is what I did right here. I dropped in 5 radical 3 times radical 3, and we multiply it out, and it comes right back to this number. This is all good for us. Does this make sense? So we're proving that this is a good answer for this pattern in this situation. Okay, I want to encourage you to go back through, take a problem you already know, and then you try to go through the steps and understand what's happening. If you don't do that, I don't know if you'll ever go sort of that next level, but for most of you, you're headed into, a higher level math. You're going to need to do some of these calculations the old school way, right? The old handwritten way of yesterday. Okay?